Okay, thank you so much, and thank you for the introduction. Uh, Today, I will, as the moderator mentioned, today I'll be talking about how we can use AI in post-event, let's say, inspection of bridges and I guess specifically bridge columns. Let me first thank my colleague, Dr. Wan, or a graduate student, you, John, Cal, and Evan. Without their help, we could not finish the project. So I had to acknowledge their directly significant contribution, and also let me acknowledge uh, the sponsors, the National Center Tri-Durley Center and South Dakota State for helping us to conduct this study. Okay, I would like also to thank the project technical panel for their comments and like feedback throughout the project, and helped us to make this research more practical. You can see the list of the panels on this screen, and I really appreciate their direct feedback. You may know that based on the current design specification, specifically the AASHTO, the seismic guide spec, we expect to see some moderate level damage in bridge columns after an earthquake. However, for rare earthquake, the bridge needs to perform in a way that the collapse is prevented. On this slide, you can see the damage of a few bridge columns after the Puerto Rico earthquake. That was 2019 and early in 2020. And I also would like to thank Dr. Call for kindly sharing these pictures to us. So that was a moderate level earthquake, and you see that the actual requirement is met. However, assume a scenario that you have hundreds of these bridges and you need to send trained people on site to assess these damages and comment on the serviceability of the bridge. So that's where we are directly headed. And here is more details of what I mean with that. On this slide, I borrowed the map from the FHWA website that shows every single bridge of the nation. We have more than 600,000 bridges in the US, and each dot in this map is one actually bridge. Those that are colored in green means that they are good, healthy, they should perform well. Those are colored in orange or yellow means that they are in fair conditions, and those in red means they are in poor conditions. Okay, approximately 45% of the US bridges are in good condition, 48 in fair condition, and only 7% are in poor condition. So far, so good. There's no issue there. But if you superimpose the bridge map with the seismicity map of the nation, you may find very interesting result. We don't have exact number. There should be a study to find the exact number, but we know that there are 16 seismic states in the nation. And if you superimpose the two maps, you will end up with 28% to 30% of the US bridges are in seismic region. And if you accept this USGS map as a let's say the hazard map for next 50 years, we would realize that 30% of the US bridges might see a damaging earthquake in next 50 years. So the number is huge, number is big, and that was like very interesting to know, at least find from our perspective. Okay, so we established that 30% of the US bridges might get damaged in next 50 years under strong earthquakes. The USGS has two tools. One is called ShakeMap, and another one is ShakeCast. ShakeMap collects the earthquake data and publishes it in real near real time in their website. So we can get data like the intensity of the earthquake and possible and potential damages and losses and stuff like that. And ShakeCast uses and input those data and map it on the bridge map, and we'll do a kind of probability analysis, and we'll figure out which bridge under that particular earthquake that just happened needs, let's say, immediate attention. So that's with higher intensity, is closer to the site, the epicenter of the earthquake, so you know which bridge you need to inspect first. But if the earthquake is large and covering a wide, let's say, region, then you have to have an army of bridge engineers to be sent to each single site to inspect the bridge. So that's the issue. And none of these tools that is out there, and there are a few others like HAZUS by the FHWA, does not do post-event assessment. They are mainly for probability, let's say, analysis, finding the weak point to take care. So it's kind of management tool rather than post-event assessment. So here is or general objective or thought process for this project. Let's say there is an earthquake, you have access to the National Bridge Inventory, and then you can use ShakeMap data, feed it into the ShakeCast, and figure out which bridges you need to inspect first. So we can do that. And then there is tons of data out there. You may obtain data including notes, videos, pictures of damaged bridges by DOT personnel. You may use satellite pictures, aircraft, or drone. You may use social media or CCTV pictures and videos, and you have all of those. Okay, our goal is to collect all of those specifically from DOT personnel, and then develop a set of tools that would allow you to perform post-earthquake assessment quick and fast. We understand that you cannot have one single tool that does everything, so you may end up with pieces like one for column, one for footing, one for the, let's say, superstructure, and do post-event assessment on each single, let's say, element, and then process and tag the bridge. Tagging in this study means you would say if the bridge is safe to be open to everyone, or should have limited access, or it should be closed to everyone. So the project, or the tools that we are looking for is maybe a cloud-based software, maybe a mobile application, or some built-in, let's say, software mount on drones. So that's where we are headed. With that, the project goal will be to expedite post-earthquake serviceability assessment of bridge columns, RC bridge columns specifically, using computer vision and also seismic analysis. So our goal is to do these things quick and fast in a moment, in a few minutes at most, so expedite the whole process. And then, rather than sending trained bridge engineers to each affected site, you may ask the local folks, the local authorized DOT folks, go there, take pictures, use that software, or send it to central office. And with these tools that I'll just explain in this presentation, we would be able to quickly assess those ones and ask those folks on site, hey, close it, or just make it open to a certain people. So that's the project goal. To be able to achieve the goals, we had to do literature review, we had to develop new damage state definitions, and develop a new test database for bridge columns, a specifically modern one, and then develop an equation or set of equations that will tell you, if you see this damage, how much bridge displaced during earthquake. So we had to do that too, and then use AI or computer vision tools to assess damages and put everything in a flowchart for computer software or computer engineers to use and program it. I will touch all of these topics, if let's say a few of those very quick and the others with more details today. So let's talk about literature review, because I'll do it piece by piece. I'll just go overall for the assessment. Visual assessment is usually the most used method after an event, specifically earthquake in this project. So because it's cheap, it's low cost, you don't need the specific tools. You send your folks to the site, they take picture, they assess the bridge based on their experience, they comment on the serviceability. So that's how it's done these days. There is no national standard on how we should assess bridges after earthquake. There are some guidelines by different DOTs, so they have different measures, different tool to comment on the serviceability. So the national guideline is missing. However, or national specification, I should say, but there is a national guideline, NCHRP 833, that performs the assessment at 4 levels. Fast reconnaissance, which is usually done with an airplane within 4 to 6 hours after the event, just to see the whole picture, the bigger picture, and graphically find if that bridge is gone or no, we should send people there. So that's fast reconnaissance. And preliminary damage assessment is when you send a person, a trained person to the site, they will assess the bridge quick and fast, and they will do a preliminary or PDA assessment numbers. Detailed one is kind of after that. So I'm showing the flow chart in the or from the NCHRP report as well here. On DDA, or detailed damage assessment, which happens sometimes after the earthquake when the PDA is done, then you may say, okay, now I can do more analysis and then have more time for inspection, so I can comment better. And if you're not happy with that, then you can do engineering assessment, or they call it extended investigation, which is case by case study. Then that would be full engineering report saying this bridge is okay or no, have to be repaired or replaced. So that's what we have: fast reconnaissance, PDA, DDA, and EI. In this project, our goal is to combine PDA and DDA using the tools that we developed in a few moments. So that would be a great advantage if possible, and I'll show that toward the end. The very first thing that we notice is the current definition of bridge column damage state is not quantitative. I'm showing a few studies that we found. Each defined the damage of bridge column with different languages and different levels and different measures to quantify that. The damage of a bridge column is basically limited. You have either cracking, spalling, rebar exposure, buckling, fracture, and core concrete. So the damage is limited. However, the range of the damage per those damage that I mentioned is not limited and is kind of subjective. So overall, any damage that you, or any damage definition that you propose is subjective and is based on the expert's opinion. So all of the list that you see here on the screen shows that subjectivity. The thing that we found is most of these languages cannot be programmed, because the definition is qualitative rather than being quantitative. So we had to develop our own damage state. We followed the one that is out there. We followed the one by the Caltrans and the one that was proposed by Belotzes, and then later by Usuri. And we followed that general 6-state damage state, which is also adopted by Caltrans, but change them to be quantitative. I will show each of those in the next slide. I just want to highlight 2 things on this slide. On damage state 1, 2, 3, you'll see I assigned a green color to it, means safe. Damage state 4 is yellow, means only first responders or light traffic can use that bridge. 5 and 6 means red, and they are unsafe, bridge should be closed. I will provide more justification on these ranges in the following slides. And also I want to mention that theta in this project which we use to quantify the crack angle, is based on the axial direction of the column and the crack angle, as you can see down on the left picture. So here is the damage state 1 damages. We expect to have only a few horizontal cracks, and theta with respect to the axial direction of the column means if your theta is bigger than 80 degrees, you can quantify that as let's say a horizontal or flexural crack. And you can see a few examples on the slide. You can only see a few 5, 6, 7 flexural horizontal cracks. Damage state 2 is where you start seeing the shear ones. To make it or measurable, we said if you have 3 diagonal let's say cracks, and each has a theta of less than 70%. And here are a few examples on this slide as well. Damage state 3, so you expect to be more extensive. We said that, okay, whenever you have a spalling, which is more than 10% of the diameter of the column, but less than 30% of diameter of the column, that would be your damage state 3. So then we are not worried about cracking anymore. We're focused on the spalling. At 4, you would see more extensive spalling, which is more than 50% of the diameter of the column. And we said to make it measurable, you should also see transverse and longitudinal bars. So spalling plus exposed bars. Okay, at damage state 5, you may see 1 bar buckled, you may see 1 bar ruptured, or you may see 2 longitudinal bars and 3 transverse bar exposed. So that would be your damage state 5, and 6 is where you see multiple buckling, multiple bar fracture in the slide. So for example, at damage state 6, the one that you see, you definitely need to close the bridge to everyone. So that's our a programmable that computer can understand damage state definition. Then we said, okay, now we have our damage state, how we can use it. The key is you need a database to evaluate and kind of find the displacement that the bridge saw during earthquake with those damages I just showed. So we need an experimental database of column performance. Here is again the list of all databases that we could find out there. So we're not the first one. The most expensive one are those by Berry and Eberhard, and which was 2008, and actually GNOME 2015. The GNOME database was built upon the work by Berry and Eberhard. So these are excellent. They have, maybe 300, 400 columns in their database. They're a good grade, but we found that they have a mix of bridge columns and building columns, 2 different animals. You cannot put them in the same batch. We also noticed that all of these databases, they include standard and substandard columns. When we say substandard columns, we mean those columns that are designed with old seismic codes, or there was no seismic code, with old codes, and modern ones are the ones that have been designed for seismic loads. So none of these databases have a pure version of the standard one that we focus on this study. So we had to make our own database as well. We did that. Our database currently has more than 200 circular columns and 68 rectangular columns in it. We also know that past experimental databases included information that had nothing to do with a bridge design and did not include parameters that were important for a bridge design. So we had to take care of those. So we proposed and developed this 300 column database following all definitions by AASHTO. So every bridge engineer in the nation then will understand what is the yielding that we're saying, what is, let's say, prime C. So basically everything has been defined per AASHTO. So 34 parameters per column were collected in the database. Database is online. You can go to this link down there, or just actually shoot me an email. I'll be more than happy to share the link with you. You can go to the Design Safe Data Depot, and then find and actually use that. So they are all in a spreadsheet and easy to use and follow with all the definitions that we discussed. Okay, so we have our database also set. Okay, now the biggest problem in this project was how you are going to figure out the displacement of the bridge after an event, because most of these bridges are not, let's say, instrumented, so you don't have any idea about yielding, about peak displacement. So how you're going to find that peak displacement after the event for successful analysis. Okay, AASHTO has three methods. We call a static method, dynamic method, or nonlinear dynamic method. So we are allowed to use per AASHTO all of these three techniques. What is available to us? We devised three methods per AASHTO, following AASHTO, to be able to estimate the earthquake level or the earthquake displacement after the event. So the first one is use the design spectrum for the affected site. The second one is to use the event spectrum for the affected site, and then perform a linear or nonlinear dynamic analysis using the event ground motion. And the fourth one, which is the focus of this study, is to relate damage that you see to the displacement using statistical analysis. So that's what we did. I'll go over each of these four quick, then we focus more on the last one. So on the method number one, there is a bridge column from National Bridge Inventory, or the estate DOT inventory. You know the lengths, the widths, the mass of the bridge. So you should be able to estimate the natural period of that column or that bend. Then you go to AASHTO, you will find your design spectrum that was specific to the site that the bridge is on and was affected with. And then you find your pseudo acceleration, then the spectral displacement. For example, if the natural period of this bridge is 0.75 seconds, this bridge will see 5.7 inches of displacement if it was in downtown Los Angeles, for example. So with that, you can estimate the displacement of the earthquake after the earthquake. Okay, there are several agencies in the US that would use the dense array of seismometers that we have to produce data after the earthquake. So one that we use in this study is CMSD database. Okay, a few minutes after the earthquake, they will process the earthquake, they will give you the ground motion, and then we have built-in, let's say, software or MATLAB codes. You can process it, and then you can get the event spectrum. What's the use for it? Then you have your spectrum, follow the technique that I said in the method one, but rather than using the design spectrum, you will use the event spectrum to estimate the displacement of the bridge column after the earthquake. The third one is more extensive. We didn't develop this, but it's kind of flowchart, or let's say architecture of a software that you might develop to do linear, nonlinear analysis. The idea is this: ground motion of that earthquake will be available to you a few minutes after the earthquake. So use that. You may use OpenSeas or any other seismic analysis software and have some pre-built, predefined column model, single column, multi-column. You put all AASHTO modeling methods there, and then right after the earthquake, you know which column it is. You have length geometry, the other properties of the column or band. Then you should be able to do linear, nonlinear analysis and get the displacement demand of that earthquake. So that would be method three. All of those are nice, doable, feasible. We didn't do the last one, or method three, but I think it's doable because we did for capacity. I'll talk about a few minutes later. But the easiest of all is method four. You can do a statistical analysis of the experimental database. You can find a relationship between, if you're seeing this damage state, this is the displacement associated with that. So I'm listing a few studies here, and the easiest, and they are doing the statistical analysis for different seismic responses. We are focused on the drift ratio The drift is lateral displacement of the column normalized length of the bridge column. So, for example, the study by Berry and Eberhard, they have, let's say, equations to find the drift of bridge column at cover spalling, drift at core crushing, and drift at bar fracture. So we have that tool. It's simple, it's easy, doesn't need any extensive engineering analysis, just needs a few parameters of the bridge column. And if you know what damage state, what kind of damage you are dealing with, you can estimate how much displacement / drift that bridge saw during that event. So we're focused on this one. We noticed that the equation by Berry and Eberhard for drift was based on a limited number of columns, the one that they had at that time 20 years ago. And so they had 20 columns, for example, at bar fracture. Now we have more than 200 columns for bar fracture. So we can update those like equations. So we did that. We followed generally the equation by Berry and Eberhard. We followed the same template, but we use our database to update them. We also made them slightly simpler by removing a few parameters that we thought won't affect the result that much. So this is simplified and final version of the equation we propose. If you are at damage state 6 for a bridge, which was, if you remember, rupture of multiple bars or buckling of multiple bars, the top equation will be the displacement or drift for circular columns, and bottom one would be for the rectangular ones based on database that we have. We could do the same thing for the other damage states 1 to 5, but we noticed that for a few of those, rather than developing a new one, you can just relate it to the next damage state. So for example, if you're at 5, there is very strong correlation. Okay, I can't remember R score here, but that was very high R score here that you could relate damage state 5 to 6 rather than developing a new equation. So if you need damage state 5, it's just 80% of damage state 6. And we repeated that for 4 and 3 at 2, which is the point that shear cracking starts. We noticed that that's very close to the yield point, and we don't have that many pictures in our database to relate that. So we borrowed the equation by Priestley, adjusted with the new database, and made one line equation for, let's say, rectangular and the circular columns to find the damage state 2. And here's kind of the summary of the entire or all the equations that we developed, plus the statistical analysis that we follow to generate these like equations. The next slide is very interesting. Here you can see 7 dots. Okay, ignore the blue one at that intersection VP. Let's focus on the other ones. Number 1, number 2, number 3, colored in basically green, are points based on the statistical analysis of database for damage state 1, 2, 3. We also know that damage state 3 is no more than 30% of damage state 6, which is the failure of the column. So if your inspector reporting damage state 1, 2, 3, that column could not see, statistically speaking, any displacement more than 30% of the failure displacement. So you have 70% reserve capacity. You may call these damage state as a safe. So that's why we colored them green. The bridge can be opened right after the earthquake if you're at damage state 1, 2, 3, and you can basically green tag the bridge to be used by everyone. At damage state 4, which is yellow tagged, you have only 50% reserve capacity before it fails. So we are calling it, okay, be cautious, it's red tagged, only light traffic and first responders can use the bridge. And damage state 5 to 6 has limited to no safety factor built in before it fails. So if your inspector is reporting 5 or 6, that bridge has to be closed. Again, this is based on the statistical analysis points. We'll move in the statistical analysis based on 1 standard deviation, 2 standard deviation. But I wanted to show this that the 6 diameter state that we proposed covers the full range of pushover, we call it, or force displacement response. And here is, I wanted to further evaluate these equations that we made for diameter state 1 to 6. There was a column that we tested here at our lab, and that was not included in the database that I discussed earlier. So that would have been a good calibration and validation of the equation. Our equation says at 0.5% drift ratio, again, drift is lateral displacement of column normalized to length of column. At 0.53% or 0.53%, you should see diameter state 1. And in fact, in testing, we saw same thing at 0.5% drift ratio. The equation predicts that 0.9% you should see yielding. We in fact saw at 0.7, slightly up but higher, which is okay for post-earthquake assessments, more conservative. The equation says you should see diameter state 3 at 2% drift ratio. We saw it at 2. Again, it's more conservative. It's okay because you're assessing the bridge for more displacements demands. The equation says at 5% drift, you should see diameter state 4. We saw the same thing. At 5 or diameter state 5 will happen at 8% drift. In the testing, we saw at 7. But here is the very interesting one. The equation says at 10% drift, this column will fail, and the column failed at 10% drift in the testing. So it was overall good validation of the proposed equation, even though developed through a statistic analysis of 200, 300 bridge columns, each tested with different ways, method, lengths, and properties. But overall, the equation is showing a reasonable accuracy for a column that was not included in the database. We can also develop equation to something called idealized yield to find that one too, or plastic forces, we can find that one too as well. Okay, we talked about diameter state. We talked about how you can estimate displacement demand during the earthquake above the capacity. At what displacement the bridge column fails. There are different techniques. The one that we adopted in this study was the one by AASHTO seismic guide. Says you need to do a pushover analysis of the column. Pushover means push the tip of the column to a point that it fails. It really, and failure means the force drops by 15%, or the core is gone, or the reinforcement are fractured. So we have ways to define the failure point. And then you will end up with a force deformation curve, as you see on top right. And you can also idealize it with 2 lines as well. That's the one that I showed in the previous slide. The pushover analysis should be done with a fiber section analysis. You need to define reinforcement as they are, where they are, and you need to define, usually we use Mander's model to define core and cover concrete with and without confinement. So we adopted this. We made a generic pushover code in OpenSeas using only 8 parameters of the column, including length, diameter, longitudinal bar, and the list goes on. And we made this generic pushover model. We picked 4 columns from database. You can see the result on the screen. The black line is measured, and the red line is the calculated response using this generic, let's say, OpenSeas pushover model. Overall, we have very good estimation and displacement capacity estimation of the model. Forces are okay, initial stiffness are okay. So we're happy with the model. So you should do a pushover analysis to estimate at what displacement your column fails, and follow AASHTO line by line. We actually made a software in cloud, basic website, and I'll show that toward the end, that using that generic bend model, right after the earthquake, you use those 8 parameters of the column, length, diameter, reinforcement, stuff like that, or tool will give you the idealized pushover of that column. So you have your capacity curve. If you find your demand, which you can do it based on the display, based on the damage state, then you can comment on the serviceability of the bridge. Okay, so far now you can estimate the displacement demand, you can estimate the displacement capacity. You need a tool to quickly evaluate the damage of a bridge column. That's where the computer vision comes in. I do not want to dive into too much and provide a lot of detail. I just want to let you know that we use a cascade flowchart or architecture, starting from column detections or AI-based tool looks for column in a picture. We didn't program it this way, but if the software fails, you may add a module that the inspector will draw a box around the column, then the software will proceed. We didn't, let's say, implement this, but it's doable. And then it will look for spalling. If it can find spalling, it will look for the cracking, but if it can't find spalling, then it will look for exposed bars, the area of the spall region, and will quantify the damage state based on our proposed definition using the extent of each of these damages. So that's overall architecture of the software. And we use two neural networks to be able to analyze the damage. The first one was mask RCNN, made for the spalling, exposed bars, and extent of those ones, and the mobile net version 2 for for the crack detection. We noticed that one is patch problem, another one is not, or is mask problem. So we had to have two different neural networks to take care of each. The user won't see any of those, just uploads the pictures and it does it automatically. So it starts again from column, spalling, and the cracking. And if it finds a spalling, then the mask RCNN software will kicks in, will take care of the rest. We had around 1,700 photos of RC bridge columns tested in laboratories. Then my colleagues kindly donated more than 1,300 pictures of the columns that they're tested, and I really appreciate their kind contribution. And then we selected more than 200 of those, used 80% for training and 20 for testing. And we went through each of those selected columns. Each had different damage, cracking, spalling, exposed bar, longitudinal, transverse bar. So we manually labeled all of those for the training purpose. For the cracking, we had more than 20,000 picture or patches of the cracking. And then we labeled them as with cracking, without cracking, and we basically trained the network with these pictures that you see, or basic sample pictures. 11,000 with crack and 9,000 without crack. What we noticed soon that overall crack is noisy animal. The crack of concrete goes around large aggregates. You do not have control on the way that it will propagate, but overall you can recognize as a human general angle for the crack. We could not do that in a computer, so we devised a histogram of let's say cracking to find the major crack of each picture. So histogram, what it does, it will find the magnitude or the gradient of the cracking in X direction, Y direction, and accumulates those and will make the histogram. And at the point that histogram hits 1, that's the angle, or that's the major angle. Don't forget that in this project, theta 0 means axial direction of the column and 90 means horizontal. So in this picture that you see, human will recognize around 0, so that's a horizontal crack. Or tool is giving us 80 degree, which is reasonable. Here it's kind of 45-degree angle, that's a cracking, or software is saying 45, human eyes will see 45 approximately without using any tool. So just upload the picture, it will tell you what is the angle of that crack. And then here Here is another steeper one, 25-degree, and we should see the same thing as well. So we are happy with this histogram of the crack, and we use this tool in our damage state. And here I'm going to show you a few results of the assessment that we did, not assessment, but the damage detection using the AI tool. Here is the list of the thing that this tool will do for you. It will give you the horizontal cracks, vertical cracks, spalled region normalized to the diameter of the column, number of horizontal bars or transverse bars, and number of the longitudinal bars. And based on the combination of those and the definition that we have, it will tell you what damage state it is. The ground truth is the one that we manually calculated, and computer vision also found similarly the same number. Both a human inspector and this computer vision tool will tell you this is damage state 1, so you are at the lower bound, or you are where that you can open the bridge. Here is result, or a few more results for damage state 1, where you expect to have only horizontal cracks. Damage state 2, you start to see shear cracks. And we went and checked the ground truths, and the one that you see on a screen by computer matched fairly well, and we ended up with the same damage state between human and the computer. So we're happy with the result. Damage state 3, that's where you start seeing spalling. That white line that you see on a screen is the maximum length in that green area or boundaries. So that would be your maximum spall length if you need that for the quantification of damage state. At damage state 4, the bars should be exposed. I'm showing a few examples. We're happy with the software is doing. It can see the column, the red box. It can see the spall region, the green boundaries, and then the blue lines are the rebar, and here is damage state 5, where you also see the longitudinal bars in the picture as well. So overall, we're happy with damage state. Computer vision tool, you need to upload to the website or to the tool. In a few moments, it will give you all of these cracks and everything, and will tell you what damage state it is. In the computer vision world, they don't work with accuracy as we usually do in, let's say, structural engineering. So I don't go into much detail. Long story short is, for every single component that we evaluated, we saw more than 90% accuracy or precision recall for all of those. So we're happy with the result of the computer vision tool. Okay, I said about all of these tools, how really you want to implement all of these in a computer program. Okay, I'm proposing performing preliminary damage assessment or detailed damage assessment. For the preliminary damage assessment is the flow chart that you see on the screen right now. You upload the picture to the software, and then computer vision tool will tell you which damage state it is based on the extent of damage. If it's from 1 to 3, means is the green tag is good to go. The bridge can be open to everyone. If it's damage state 4, only first responders or light traffic can use it. And if it's damage state 5 to 6, no safety, you have to close the bridge to everyone. So you just need to upload the picture. The software will do the rest for you, or does the rest for you. If you want to do more detailed analysis, then you need to bring in seismic analysis. The computer vision tool, you need to upload there. I'll talk about that in a moment, but you also need to do pushover analysis to get the capacity curve of the column. Using the OpenSeas model, the generic model that I showed you, and a few column parameters, you can figure out at what displacement the column yields, at what displacement it fails. Then you go to computer vision tool, it will tell you damage state. Then you will use one of those 6 equations that I showed you earlier. You will estimate how much displacement that column saw during that earthquake. You will map it to the capacity curve based on the ratio of the red dot to the ultimate point. You can comment on the serviceability. So there should be a range of performance here, and we are proposing the range of, if that ratio is less than 0.5, 0.4, it's inspected, it's good, can be open. between 0.4 and 0.65 is limited. And if it's more than 0.65, it's unsafe. It's subjective, we understand that, but as a user, you might adjust that based on your experience, so software can allow you. So these are default values. If you're not happy with those, you should be able to change those as well. And it will tag the bridge for you. So all is happening in a few moments. Upload picture, it does the rest for you. I talked about you need a range of performance for detailed damage assessment. We are going based on the average of the limits that we have, and those number that you saw is based on the average. Okay, here is our tool. You can go to our website, still under development. There are new, I need to do we need to do a few final touches, but it's there. The home page is just journal description. Preliminary damage assessment is the one that will does damage assessment for you, and detailed damage assessment. You can go to website, upload the picture of column. It will tell you all of those details that I discussed earlier, and it will tell you if the bridge is safe to be open. If not, if you want to do more detailed analysis, you go to that tab, upload your picture. It will ask a few column parameters, 8 or 9 of those. Then it will run, let's say OpenSeas behind the scene, will give you the pushover analysis, and will tell you based on the damage and the capacity if this bridge is safe or not safe to be open to public or not. So based on the 3 limits that we have, we should be able to do that. So that's our website. So with this slide, I conclude the presentation. I think all of those modules that we did were necessary to make that flowchart feasible and possible, and to showcase that it's doable. We made that online tool to show that all of these is possible. It's not, let's say, at the commercial level at all. It's a research tool, needs a lot of work to be commercialized if you want to do later. But the whole point was it's doable. We can combine seismic analysis with computer vision to expedite post-earthquake assessment. So with that, I'll stop, and I will open the floor for any questions that you might have. Thank you.
Hi, Mostafa, this is Muhammad Ashur. How are you? It's a great presentation. I really enjoyed this presentation. I have a couple of quick questions for you. I might join the presentation maybe 10 minutes late. When you are creating your or developing your estimates for the damage level, I noticed that you account for the cracks, the angle of cracks, the length of the cracks, things like this. Did you account for the depth of the crack? I might have missed this one, but I did not notice this.
No, that's actually a very good question. The crack widths, let's say after earthquake, is not a good indicator. The reason being is the crack is wider at the peak displacement of the column, and after the earthquake, column comes back. So you do not have a clear measure, or what you see after the earthquake is not indicator of the big displacement. So we did not include the widths of.
No, I mean the depth. No, I mean the depth of the crack itself, the penetration of the crack into the column itself.
No. We need to be quick. These analyses are just to expedite post-earthquake assessment. Is not to replace detailed assessment. So no, our goal is to find how many shear and vertical cracks you have, or let's say horizontal and vertical one you have, and go to the damage state, say what damage state it is.
Okay. The other question that I have it here about the drift ratio and the calculation. I noticed that, or we know that most of the data that we collect for experimental data, they are coming from columns tested based on fixed pace in the labs. So in this case, but in reality, when we have it, you are going to have your columns as shaft columns, piles, or shallow foundation. I mean, that which is not common. Of course, the shallow foundation is state of California or Washington for rocking. So this is going to affect your drift ratio, that the one that you calculated. So how do you guys handle this?
Very good question. We went with all test data, and usually in test, as you mentioned, they're all fixed base. We did not change these numbers based on the fixity or basically anything like that, because our goal was again to do a quick demand analysis at this level. You see this damage. This damage is related to 5%, 4%, 5 inches of displacement. So that's actually what we did. We did not soften the model or these parameters to include soil or soil structure interaction or anything like that. So these are all based on fixed based.
Okay, thank you.
Do we have
as long as there is nobody ask question, let me add a third one. So
sure, absolutely.
So what's your definition for failure when you said that we go in the field and check it for failure? The failure that you mean here, that failure if you keep the bridge running without being hit by any new earthquake, or just a preparation for the next earthquake that could cause the kind of serious failure?
Perfect.
So what's
perfect? Yes. So there are two definitions for failure. The first one I probably can go and to the slide. I probably don't have it here. There are two failure. One is what you see, and one is what you analyze. So as, let's say, inspector, the failure means you see multiple bar buckling, multiple bar rupture, or your bridge column is kind of deformed, as you can see on the screen under the dynamic tab. So if you see large residual displacement that cannot be recovered after earthquake, your bridge deck is kind of tilted significantly, no one can pass along, or you see multiple column or a bar rupture / buckling, then that's your field failure. For the analysis, there is no definition of failure by AASHTO, but the general definition by the experts is that whenever your force capacity drops by 15% with respect to the peak one, so that's your failure point. There can be multiple reasons for that: P delta effect, again, bar rupture, core concrete crushing. But as soon as you reach 15% drop, that's where you need to stop your analysis. I think in the pushover analysis, that's what we did, or here even in the test, that's where we stopped the test, because you reach 15% drop with respect to the big one, and all of these will be in line with that.
Thanks.
Yeah, thank you.
Thank you, Dr. Archer. So we got another few questions from the chat box. The first one is that, does the magnitude of the earthquake change anything in the calculation or measurements?
The magnitude of earthquake will definitely, if it's higher, you will see more damage, more extensive damage. Then you will bump up your damage state as the damage is. And we made enough safety tools and measures into our calculation that you might be really at damage state 1 or between 1 or 2, but then our software will give you 2. So you're assessing your bridge for more extensive, let's say, demand. So you are staying on the safe side of the analysis.
Sure, thank you. And how would pictures work at night or those underwater?
At this time, we don't have, or we didn't train the network to take care of underwater or at dark. We might be able to use something else like the LiDAR or maybe infrared later and train the network for it. But within the database that we have, we only have laboratory test pictures. We train it for it, so it only works with real life, nice lighting. You cannot do really dark ones, and your entire column or the majority of that should be in the picture. So all of those limitation applies here.
Sure. And would the crack detection be equally efficient if the column is painted or is covered with algae or planet on it?
Okay, very good question. I think we did a few ones on the one that is painted or with algae on it. As long as there is a crack that human eyes can see it, that should be able to see it too. So if I go to maybe some of those examples, that would be very interesting to talk about those. Let's say go to the cracking here. On the right side, so that's a laboratory testing, or on, let's say on the left side, you see wires from the LVDTs, you see let's say a steel bar, you see someone's hand with the board there. It's not seeing any of those as a crack. Also, there is a cable on top corner, and there is also sonotube, the construction mark on the column on both sides, vertical one on the right and horizontal ones on the left, and is not seeing any of those as a cracking.
Okay, okay. Thank you, Dr.
Sure, thank you.
And what are the average cost in terms of calculation time, computation power, and calibration of the proposed parameter, particularly the 8 parameters used in the pushover test for the models?
Okay, pushover test doesn't take any time on a laptop, maybe 5 seconds. Less than that, you hit the button and it will give you the result. But the computer vision on laptop with 8 gig of GPU will take 1 to 2 minutes. We're trying to move this on a school server, so hoping that the school server is at, let's say, commercial level, so everything should be faster. We haven't seen that yet, but on laptop, 2 minutes for post-processing all of these pictures.
Okay, the last one. For a column with DS labeled green, how would this historic loading of the column be considered during next inspection?
Can you please repeat the question?
Sure. For a column with DS labeled green, how would this historic loading of the column be considered during next inspection?
I don't think we did include that. There is a burst, there is a damage. You go there, use this tool, it will give you damage state. It doesn't include the history of the column. It doesn't include whatever is coming next. It just, whatever it is you see there, it will tell you if it's usable or should be closed. That's all it does. It doesn't include any loading history or anything like that.
Okay, great. So thank you, Dr. Tazarv. Thank you, everybody, for joining this great webinar. And it's very impressive and interesting. So I hope you guys all enjoyed it and have a good day.
Sure. Thank you so much for your time, everyone. I really appreciate it.
Thank you. Bye-bye.